When we're learning statistics, we learn a lot of distributions, and there are a whole bunch of distributions that are just part and parcel of learning the statistical processes. So the normal distribution, for instance, or on the discrete side, the Poisson, or the binomial, hypergeometric. On the continuous side, beyond the normal, the exponential, the Weibull, the gamma. There's all these distributions in statistics, and we end up learning how to map our data to them. What we'd spend a little less time talking about often in statistics is that there's any number of distributions out there that can be used to make predictions that don't have their roots in basic statistics or statistical analysis. That doesn't invalidate their use. I mean, if you can correlate the data in your process to show that it follows the M1 money supply or housing starts or the stock market price, and correlate your data to information like that, you're perfectly within your rights to use those curves and distributions to make predictions about your process if you can show that it fits. So realistically in statistics, we're learning a process for making predictions after fitting our data to a curve or to a distribution. There's no absolute requirement that it be one of the main statistical distributions. Those are the ones we talk about the most. But in fact, this logic applies to a lot of other things. Here's an example called Benford's law. It's a who. Dr. Benford came up with an analysis that showed that when he analyzes sets of numbers, say data sets, so all of the dollar amounts that would show up in someone's tax return, all of the dollar amounts that would show up in a financial statement from a company, all the dollar amounts that might be in your financial history, all the dollar amounts that might occur in Amazon sales transactions for the day. Take a large set of numbers representing financial data, and it turns out that data is not randomly distributed, and there's a set description of how that data will fall. And what Benford found was that the first digit of the number follows a very distinct pattern that can be discerned. The first digit of any financial number in a ledger is much more likely to be a 1 than a 2, more likely to be a 2 than a 3. In fact, it turns out, looking at these distributions, that the predictions made by Benford in the model are that of all the financial numbers, say, in a database of finances, 30%, the first digit will be a 1. It makes no difference if the number is a $10 number, a $1,000 number, a $100,000 number. We're only talking about the very first digit. It turns out there's about a 17 to 18% chance that the first digit will be a 2. There's about a 13% chance that the first digit will be a 3, and so you've got a set distribution. Here you're seeing in this red curve the way that looks. It looks very exponential, if you will. It's a declining average. The number 1 is much more likely to be the first digit of a financial number than, say, the number 8. Now, this spreadsheet that I'm sharing with you, I downloaded from this one site, so I've cited it here so that you can go and read about it if you want. I'm going to give them credit for their spreadsheet. But it came with some data plugged in, some sample data plugged into the data set that just came plugged in. So here's a distribution of 66 data points they use to illustrate that. If you're not used to Excel and you're wondering where this first digit came from, the formula for that is simply to do a left function looking at the numbers. So left, looking at A10, take just that first digit, and that will return the first digit of the number, no matter how many digits are there. So, for instance, it picks up the 7 on the larger number and the 4 here on the smaller number, and it's just fine. Then the spreadsheet simply calculates how many of those occur. So here's an example where the distribution in red is the curve we're looking for, and the blue is what actually occurred in this data. It's not a perfect fit, but it's a good fit. We're missing maybe some fit data, but it's a lot more 1s than 2s, more 2s than 3s. In fact, they're higher than would be predicted, so maybe I would have thought some of those would be 3s. So, but more or less, this data fits a Benford's law curve. So if I were comparing 5 data sets and this were the worst fit, this might be the one that I look at. But let's take it just to illustrate how that works. Let's use a different curve as we go through. If I were to create a new data set, shrink that down. Don't need to watch my video. Okay, a blank worksheet. If I just were to create some random data, so let's say I want to trick the IRS into accepting my tax return. So what I do is I come in here and I generate a random variable. I'm going to use 66 values because that's what the thing had. I'm going to make it a uniform distribution because I'm thinking to myself that if I want the data to look random, I should make all the digits occur pretty much the same. So I'm going to take the numbers maybe from $1,000 up to 9999. And I'm thinking I can outsmart the IRS by generating a lot of random data that I then use in my data set. So I'm going to put the data right here in the first cell. I'm going to run that. Okay, so I've generated 66 random data points going through, and I'm going to bring that now over to the other data set, and I'm going to paste it into the model. So this original set that came with the spreadsheet was a reasonable fit. The blue data shows it's not perfect, but it does in fact tend to obey Benford's law. Now let's plug in my data, and look what happens. The data now doesn't. It in no way reflects what you would have expected out of Benford's law. So that's why the IRS or a financial auditor can instantly spot that the data in this data set's been more or less randomly generated. It isn't real financial data because real data follows Benford's law as you go through. So that's the power of a distribution as you go through, is that these distributions can be used in different ways. If you're curious about where the numbers come from, go out to some of the websites and read about Benford's law, and you'll see where that basically comes from. But the basic gist of it makes a lot of sense. If you think about financial numbers, whether it's $1,000 or $10,000, if the first digit is a 1, you more or less have to double that amount before it changes into a 2. So it takes a lot of change to drive a 1 to a 2. Once you've got a 2 in the first position, the number only has to grow by 50% to turn it into a 3. It's easier to get from a 2 to a 3 than it was from a 1 to a 2, and that works its way up the cycle. If I've already got a 3, I only have to increase it by a third to get to a 4. If I've got a 4, it's only by a quarter to get to a 5. So every number I go up the scale, it requires less change in the number to kick it into that next digit, which is one of the reasons you would expect that a 1 will be most common, a 2 will be next common. So the red curve can in fact be explained if you think about what's happening in financial data. So here's a set of data I generated trying to trick the IRS by plugging random data into my distribution, but as you can see, it shows up in the curve. It almost looks like a uniform distribution. It's not completely uniform because I used a uniform distribution to generate the data, but it only generated 66 data points. If I generated 1,000 data points or 10,000 data points, these blue bars would all be the same height because I was randomly distributing the data. So the algorithm I used to generate the fake data doesn't fit the logic that actually applies to financial data when it's in a database. So the fact that this data does not fit the curve, for all I know, will trigger an audit at the IRS, or it will trigger some kind of a process to go on, because clearly this isn't real financial data going on in the process. That's the power of fitting data to curves. So as you think about fitting your data to a statistical distribution, don't just think in terms of the few statistical distributions that we actually process in a statistics class. Think about any distribution you can come up with that would have a sound basis of logic behind it.